What would it mean if a hole opened up on the surface of our sun, large enough to swallow 24 Earths placed side by side? Recently, that's exactly what astronomers observed. A vast, butterfly-shaped opening in the sun's outer atmosphere, or corona, stretching nearly 300,000 kilometers across. This coronal hole is one of the largest seen in recent years. But what exactly is a coronal hole? Despite the dramatic name, it isn't a physical void in the sun's body. Rather, it is a region where the sun's magnetic field lines open out into space instead of looping back to the surface. Normally, the corona is threaded with closed magnetic loops that trap hot plasma. But in coronal holes, those loops break open, and charged particles stream away freely into the solar system. This phenomenon was detected between the 8th of September and 11th by NASA's Solar Dynamics Observatory, or SDO. Using ultraviolet imaging, the SDO recorded the dark, wing-like structure spreading across the corona. Against the sun's brilliant glow, these regions appear almost black, not because they are cooler than the rest of the corona, but because they are less dense and allow us to see deeper into the sun's layers. The size is staggering. More than 23 Earths could be lined up within its width. That scale is difficult to imagine, especially when we recall that our entire planet is already tiny compared to the Sunday. For perspective, the sun's diameter is about 109 times that of Earth. Yet this single coronal feature spans nearly a quarter of that diameter. Why does this matter? Because openings of this scale allow torrents of solar wind to escape at speeds exceeding 700 kilometers per second. The solar wind is a constant outflow of charged particles, mainly electrons and protons, that flows from the sun in all directions. But when guided through coronal holes, the outflow is faster, denser, and more concentrated. Such streams can travel across the 150 million kilometers between the sun and Earth in just a few days. And when they arrive, they interact with Earth's magnetic field in ways that can be both beautiful and disruptive. This is not the first time coronal holes have commanded attention. Back in March 2023, another enormous hole, spanning 300,000 kilometers, opened on the sun, generating widespread discussions about potential impacts on Earth. Events like these remind us that our star is not a static ball of light, it is a dynamic, turbulent furnace, constantly shifting and reshaping its magnetic surface. The butterfly-shaped hole of September 2025 is just the latest chapter in that ongoing story. But what makes it particularly significant is that its outflow is directed squarely toward Earth. Within days of its detection, scientists predicted that streams of fast solar wind would be arriving at our planet, possibly triggering geomagnetic activity in our atmosphere. So what happens when these charged particles collide with Earth's magnetic shield? That's the question we'll explore next. When a coronal hole opens directly facing Earth, the streams of solar wind it releases are not just flung into the void, they are aimed directly at us. And once they begin their journey, there is little that can deflect them. The solar wind from the butterfly-shaped hole, observed in September 2025, was expected to reach Earth by the 14th of the month. Traveling at hundreds of kilometers per second, these charged particles move across the space between the Sun and Earth in just a few days. But what exactly happens when this stream arrives? Earth is surrounded by a protective magnetic field, generated by the molten iron churning in its core. This magnetosphere acts as a shield, deflecting most of the incoming solar particles. Yet, when the solar wind is strong, it can buffet and compress this magnetic shield. The result is a geomagnetic storm, disturbances in the near-Earth environment that ripple through our planet's upper atmosphere. Scientists classify these storms using a scale that runs from G1 to G5. G1 represents a minor event with only localized effects. G5 represents the most extreme storms, capable of causing widespread technological disruptions. The storm expected from this event was forecast to fall between G1 and G2, mild to moderate. That means we can anticipate some minor disturbances, but nothing that threatens the global infrastructure of our civilization. Still, the scale of past events reminds us of what is possible. In 1859, the famous Carrington event unleashed a geomagnetic storm so powerful that telegraph systems across Europe and North America caught fire, and auroras were seen as far south as the Caribbean. In March 1989, a weaker but still intense storm caused the collapse of Quebec's power grid in Canada, leaving millions without electricity. Compared to these historic storms, the current solar event is relatively modest. Yet it serves as a reminder of how interconnected we are with the star at the center of our solar system. When the sun stirs, Earth feels it. But there is also a side of these storms that is not destructive at all. In fact, it is breathtakingly beautiful. To understand why, we must look at what happens when solar particles slip past Earth's defenses and ignite the skies. When streams of solar wind slam into Earth's magnetic shield, most of the energy is deflected back into space. But a fraction of those charged particles slip down along the magnetic field lines, funneled toward the planet's poles. There, at altitudes between 100 and 400 kilometers, they collide with atoms and molecules in the upper atmosphere. The result is one of nature's most spectacular light shows, the aurora. Electrons and protons from the solar wind excite oxygen and nitrogen high in the atmosphere. As these atoms return to their normal energy states, they emit light. The colors depend on which gas is struck and at what altitude. Oxygen glows green and sometimes red, while nitrogen can produce shades of blue and purple. Together, they create rippling curtains of light that shimmer across the night sky. The timing of this recent coronal hole coincides with an important astronomical moment, the September equinox. Around both the March and September equinoxes, Earth's tilt positions its magnetic field in such a way that it couples more efficiently with the solar wind. In practical terms, this means geomagnetic disturbances are more likely and auroras are more intense. During equinox seasons, for people living at high latitudes in Canada, Scandinavia, Alaska, and Antarctica, this creates the perfect conditions to witness vivid auroral displays. During strong storms, the lights can spread to lower latitudes as well. On rare occasions, they have been seen as far south as the Mediterranean or central United States. In the days following the 14th of September, skywatchers near the poles were advised to keep an eye on the night sky. Even though this storm was expected to remain mild, its equinox timing meant the auroras could be brighter and more widespread than usual. To observers on the ground, auroras are not just a spectacle. They are a visible reminder of the vast electromagnetic interactions between Earth and its parent star. They connect us visually and physically to the sun's restless activity. But while these lights are harmless and mesmerizing, geomagnetic storms also carry risks for our modern, technology-dependent world. That is what we turn to next. The beauty of auroras often masks the hidden reality. Geomagnetic storms, even at moderate levels, can interfere with the technologies our society depends on. When solar wind particles compress Earth's magnetic field, they induce electric currents in the upper atmosphere. These disturbances, in turn, can disrupt the radio waves and satellite signals we rely on for communication and navigation. High-frequency radio, used by aircraft flying over polar regions, can fade or cut out entirely during strong storms. GPS systems, which depend on signals passing through the ionosphere, can lose accuracy. Satellites orbiting above Earth are also vulnerable. Charged particles can penetrate their electronics, causing malfunctions or shortening their lifespans. In 2003, a series of solar storms temporarily disabled several satellites, including some used for weather monitoring. In extreme cases, solar storms can even alter satellite orbits by heating and expanding Earth's upper atmosphere. increasing atmospheric drag. Closer to the ground, power grids are perhaps the most critical infrastructure at risk. When geomagnetic storms induce currents in long transmission lines, transformers can overheat and fail. This is what happened in March 1989, when a geomagnetic storm triggered a province-wide blackout in Quebec, plunging millions of people into darkness for hours. Fortunately, the storm generated by the butterfly-shaped coronal hole was classified between G1 and G2. At this level, effects are usually limited. Weak power fluctuations, occasional impacts on high-latitude power systems, and minor disruptions to satellite operations. For most of us, the most noticeable consequence will be brighter auroras dancing across the night sky. Still, the sun reminds us that even mild events deserve attention. As our technology grows ever more interconnected and reliant on satellites and electricity, our vulnerability to solar activity increases. Modern monitoring systems, such as those operated by NASA and NOAA, provide warnings hours or days in advance, giving power operators and satellite controllers a chance to prepare. In this case, scientists emphasized there was no cause for alarm. But they also acknowledged the importance of vigilance. The sun is a dynamic star, and while most events are mild, history shows us that severe storms are possible. Having examined this solar event, we now turn to a very different kind of mystery, one not from our sun, but from here on Earth. A strange object captured in footage from Yemen that has sparked intense debate. Not all mysteries in space science come from distant stars. Sometimes they appear much closer to home, caught on shaky footage in conflict zones. Recently, a video surfaced from Yemen shown during a public hearing on unidentified aerial phenomena. The footage depicts a military missile intercepting an airborne object. At the moment of impact, something unexpected happens. 3 smaller objects appear to emerge from inside the main body, scattering outward and continuing to fly independently. On social media platforms like Reddit, the video ignited speculation. Some viewers claimed it showed undeniable evidence of an unidentified craft releasing controlled components rather than breaking apart chaotically. The fact that the fragments appeared similar in size and moved in distinct trajectories was, to many, deeply unusual. The footage was captured in infrared, adding to the sense of mystery. Infrared cameras detect heat signatures, not visible light, so the scene appears in glowing shades rather than familiar colors. The 3 emerging objects shared nearly identical infrared patterns, suggesting they were of similar composition or temperature. To UFO enthusiasts, this was a sign of intelligent design, but skepticism quickly followed. Analysts pointed out that conflict zones are filled with experimental military hardware, drones, balloons, and decoys. Each of these could produce footage that looks strange to an untrained eye. Without verified provenance, any recording must be treated with caution. Indeed, US officials have not confirmed the video's origin. It was reportedly passed to lawmakers by an anonymous whistleblower, and without a clear chain of custody, there is no way to guarantee authenticity. Still, the Yemen video remains one of the most circulated in recent months. To understand whether it truly depicts something anomalous, we need to compare it with documented events involving known objects under similar conditions. That comparison offers revealing clues, which we will examine next. To understand what the Yemen footage may represent, analysts turned to comparison. And when they did, one example stood out. In 2023, a high-altitude balloon launched by China was intercepted over North America. Footage of the strike, both in visible light and infrared, shows the balloon breaking apart, shedding multiple fragments. At first glance, those fragments seem to move independently, much like what was reported in the Yemen video. The resemblance is striking. Both cases involve an object struck by a missile, Both show smaller pieces separating in patterns that look deliberate, and in both, viewers speculated that the fragments might be something more than simple debris. But aerospace experts emphasize that this behavior is consistent with balloons or lightweight drones. When the thin outer shell is ruptured, internal components such as gas tanks, payload packages, or structural braces can detach and fall away. Under reduced air pressure at high altitude, these pieces can drift apart smoothly, creating the illusion of coordinated motion. Some commentators suggested the Yemen object could have been a drone, given the prevalence of unmanned systems in modern conflict zones. Others lean toward the explanation of a balloon used for target practice or surveillance. Balloons are inexpensive, difficult to detect, and often employed for testing anti-aircraft systems. Crucially, the origin of the Yemen footage remains uncertain. It was introduced to the public by an intermediary, not by a verified military source. Without authentication, it is impossible to know whether the video shows an extraordinary event or a misinterpreted conventional one. Science demands caution. The lack of verifiable data means the most rational approach is to compare the event with known examples, and in doing so, the balance of evidence points to familiar explanations, not alien ones. Yet, while Earth grapples with mysteries in its own skies, astronomers are tracking something far stranger, an object from deep space that defies nearly every expectation. It is called 13 Atlas. From unexplained objects in Earth's skies, we now move millions of kilometers outward to a body that has captured the attention of astronomers worldwide. Its name is 13 Atlas, formally catalogued as C, divided by 2025 P1. On the 21st of July 2025, the Hubble Space Telescope turned its gaze toward this interstellar visitor. What it recorded challenged almost everything we know about comets. The images revealed a brilliant streak of light extending not away from the Sun, but directly toward it. This unusual feature was quickly labeled an anti-tail. To understand why this is remarkable, we need to recall how comets behave. As a comet approaches the Sun, radiation and solar wind heat its nucleus, releasing gas and dust that form a tail. Radiation pressure pushes this tail away from the Sun, regardless of the comet's direction of travel. This is so consistent that tails always point away from the Sun even when the comet is moving outward. But 13 Atlas was different. Its elongated feature stretched 10 times longer toward the Sun than in any other direction. This was not a trick of perspective. Even after accounting for Earth's viewing angle, the geometry still showed a beam-like extension facing inward. Such behavior has never been observed in a comet before. The discovery was made by Avi Loeb and his colleague, Amir Siraj, who analyzed the Hubble data. Their conclusion was clear. The brightness and elongation of the feature could not be explained by ordinary cometary physics. Instead, it suggested something unprecedented. For astronomers, this was a moment of both excitement and caution. Objects arriving from interstellar space are already rare. Only two had ever been observed before: Oumuamua in 2017 and Borisov in 2019. Both challenged expectations in their own ways. But 13 Atlas seemed to combine multiple anomalies into one object. It was not merely another comet passing through, it was an enigma demanding closer study. And as researchers examined the data, they identified not one anomaly, but 5 each, more puzzling than the last. When scientists compiled the observational data from 13 Atlas, they realized it wasn't just unusual in one respect, it broke the rules in 5 distinct ways. Each of these anomalies alone would be enough to raise eyebrows. Together, they make 13 Atlas one of the strangest objects ever observed in our solar system. First anomaly, its trajectory. 13 Atlas follows a retrograde orbit, meaning it moves in the opposite direction of most planets around the Sunday. Yet despite this, its path lies remarkably close to the plane of the solar system, the ecliptic, deviating by only about 5 degrees. The probability of such a precise alignment happening by chance is estimated at about 1 in 500. This path will also bring the object near the orbits of Mars, Venus, and even Jupiter in the coming years. Second anomaly, its size. Initial estimates suggest the nucleus could span as much as 46 kilometers in diameter, colossal, compared to other known interstellar visitors. For comparison, Oumuamua was only a few hundred meters long, and Borisov was about 1 kilometer. If confirmed, 13 Atlas would be up to 1 million times more massive than Borisov, making it the largest interstellar body ever detected passing through our neighborhood. Third anomaly, its brightness toward the Sunday. From the moment of discovery, 13 Atlas displayed a persistent glow extending sunward. At distances between 3 and 4.5 astronomical units from the Sun, that's 3 to 4.5 times the distance from Earth to the Sun, its light still stretched inward. No other comet has shown this behavior. Normally, radiation pressure from the Sun pushes dust and gas away, not toward it. Fourth anomaly, its chemical composition. Spectral analysis revealed that the gases escaping from 13 Atlas are dominated by carbon dioxide, about 87%. Carbon monoxide accounts for another 9%, while water vapor, usually abundant in comets, makes up only about 4%. Even more puzzling was the detection of nickel without the usual accompanying iron, as well as cyanide compounds. Some researchers caution that iron may simply be harder to detect because it requires higher temperatures to vaporize. Still, the chemistry does not match any standard comet profile. Fifth anomaly, its polarization of light. When sunlight reflects off cometary dust, it becomes polarized. Astronomers measure this polarization to study the size and composition of particles. 13 Atlas, however, showed a deep negative polarization at very small phase angles, unlike anything seen in solar system or previous interstellar comets. This unique signature might be tied to the extraordinary beam of light extending toward the Sunday. Individually, each of these anomalies would mark 13 Atlas as a noteworthy object. Combined, they position it as a mystery of the highest order. Astronomers are now debating what it means. Is 13 Atlas simply a rare but natural type of comet that we have never seen before? Or is it something entirely new, an object that doesn't fit into any of our current categories? To explore that question, we must examine the competing explanations. Some scientists argue for unusual but natural origins, while others suggest we may be witnessing a phenomenon that defies classification. Faced with such anomalies, the scientific community is cautious. The first step is always to search for natural explanations, even when the data looks unprecedented. One proposal is that 13 Atlas is shedding unusually large fragments of ice. Normally, comet dust consists of tiny particles that are quickly blown away by solar radiation. But in this case, larger, denser pieces may be surviving much farther from the nucleus. These fragments could scatter light in a way that produces the strange anti-tail pointing toward the Sunday. Another explanation focuses on chemistry. The dominance of carbon dioxide and carbon monoxide, along with unusual metallic traces, suggests that 13 Atlas may have formed in an environment very different from the outer solar system. Perhaps it originated around another star where conditions allowed exotic mixtures of ice and metal to condense. If so, studying it could provide rare insight into the diversity of planetary systems across the galaxy. Still, some anomalies resist easy categorization. The retrograde orbit aligned with the ecliptic, for instance, is an unlikely coincidence. While improbable, it is not impossible. Space is vast, and given enough time, rare alignments can occur. But the combination of trajectory, chemistry, brightness, and polarization makes 13 Atlas difficult to explain with known models alone. This has led a few voices, most notably Avi Loeb of Harvard University, to suggest that we should not rule out extraordinary possibilities. Loeb is known for his willingness to consider that some interstellar objects might be artificial in origin. In the case of 13 Atlas, he has emphasized that the anomalies deserve rigorous investigation, though he also acknowledges that natural explanations may ultimately prove correct. The debate reflects the core of the scientific method: to remain skeptical, but open-minded. Extraordinary claims require extraordinary evidence. For now, the evidence points to an object of unusual natural origin, but one that challenges our existing categories. What matters most is that we continue to study it. And fortunately, we won't have to wait long for more data. Observations in the near future may help resolve at least some of these mysteries. The mystery of 13 Atlas will not be solved by speculation alone. Fortunately, a rare opportunity is approaching, one that could bring us closer to understanding this unusual visitor. In October 2025, NASA's Mars Reconnaissance Orbiter will turn its HiRISE camera toward 13 Atlas. HiRISE is one of the most powerful imaging instruments ever sent beyond Earth, capable of resolving surface features on Mars just a few meters across. When trained on 13 Atlas, it could provide estimates of the nucleus size with far greater precision than Earth-based telescopes. If the nucleus truly spans 46 kilometers, HiRISE may confirm it. If smaller, we may rule out some of the more extreme scenarios. Other observatories, both ground-based and space-based, will also continue tracking the object. Spectral measurements may refine our understanding of its chemistry. Polarization studies may reveal whether its unusual light scattering is caused by exotic dust grains, large ice fragments, or something entirely new. Each piece of data brings us closer to an answer, but there is urgency. Interstellar objects pass quickly. Oumuamua was visible for only a few weeks before fading into the darkness. Borisov remained observable for longer, but it too has disappeared into interstellar space. 13 Atlas will eventually do the same. The window to study it is limited. That is why scientists emphasize the need to use every available tool now. Telescopes across the world and in orbit are being directed toward it, and proposals are already circulating for dedicated observation campaigns. Some even argue that we should prepare rapid response missions in the future spacecraft ready to intercept the next interstellar visitor at short notice. For now, though, we watch. And we wait. Because while the sun reminds us of its power through auroras and storms, interstellar objects like 13 Atlas remind us of something else: how little we truly know about what lies beyond. They are silent messengers from other star systems, carrying within them the secrets of alien worlds. What might 13 Atlas reveal before it slips away into the dark? And how many other such travelers are out there, crossing the void, unnoticed? That remains a question for the future.